Another very common use of induction is to prove solutions to recurrence relations. We haven't formally discussed recurrence relations yet, but you can think of recurrence relations as recursive descriptions of sequences. So here's an example. Um, Let A sub n, where n ranges over the natural numbers, be a sequence that is defined with an initial condition. The very first element of this sequence is a naught equals 1, and it has a recursive description. A sub n is equal to an minus 1 times n. So what are some of the entries of this sequence? Well, we know that a naught is equal to 1, then a1 is equal to 1 times 1, a2 is equal to 1 times 2, a3 is equal to 2 times 3, which is 6, a4 is equal to 6 times 4, which is 24, and so on. So this is a sequence that's defined in terms of a recursive description. Can we get an explicit formula describing this sequence? And the answer is yes. So theorem, for all n, it's the case that a sub n is equal to n factorial. N factorial, where remember, n factorial is defined in the following way. So n factorial is 1 if n equals 0. This is just by convention. And then n factorial is equal to the product of everything from I equals 1 up to n of I if n is greater than or equal to 1. So we can prove this theorem. We can prove that the sequence described by this recursive description is the sequence of factorials. A sub n equals n factorial for all n. How do we prove this? So for our base case, we just need to check n equals 0. So we can check, okay, a naught is equal to 1, that's in our initial condition, and that's equal to 0 factorial by definition. Or by convention, if you want to think about it that way, by convention or definition, either way, 0 factorial is equal to 1, and so we have established our base case. Now, for our inductive step, this is going to go very similarly to many other inductive steps we've seen. So assume that the statement is true for some choice of n equals k. So I'm going to assume that a sub k equals k factorial for some k greater than or equal to 0. Then let's do a direct calculation to show what ak plus 1 has to be. So ak plus 1. Well, ak plus 1, by the recurrence relation that we've been studying, is equal to k plus 1 times a sub k. That's by this recursive description of the sequence. Okay, next, we know that a sub k is actually equal to k factorial. So let's unpack and justify these two steps. So first step, so this is the recursive definition of the sequence. This second step is the inductive hypothesis. Okay, so now we can keep going here. So what do we know about k factorial? Well, this is k plus 1, and then I'm going to put my cases here. This is 1 if k is equal to 0, and the product of I equals 1 up to k of all the integers I, when k is greater than 1, so that's the definition of the factorial function. Then I'm just going to pass in my k plus 1 into here. Okay, so I have two cases. In the case k equals 0, k plus 1 is equal to 1, and so I'm looking at 1 plus 1. So here we are 1 if k is 0 again. And then down here, I equals 1 up to k plus 1 of I in the case of k greater than or equal to 1. So that is algebra. And here what's happened is that I took my k plus 1 and I just folded it into the index of the product up here. Okay, but guess what? This last expression, this agrees with the definition of k plus 1 factorial. So I have shown that a sub k plus 1 is equal to k plus 1 factorial. As a consequence of my inductive hypothesis, a sub k is equal to k factorial. And so I have completed my inductive step and my proof. This kind of proof that a certain kind of function solves a recurrence relation, a recursive description of a sequence, is especially common when we're studying the runtime of algorithms. Often we have a recursive description of the runtime of an algorithm, and we use an argument like this in order to give a more explicit description of how long that algorithm is going to take to run. And we're going to talk more about that soon.